It is Agresti from University of Roma,
Yes.
and she's going to talk about quantum violation of an instrumental test. Okay,
Thank you. So, good morning. So, as you heard, I'm from Rome, from the experimental group of Fabio Sciarrino. And today I'm going to talk about this work that was carried out within a collaboration between Rome, Rafael Chavez and Leandro Olita. And what we did in this work is we showed both theoretically and experimentally that in the case of instrumental processes, which I will introduce in the next few slides, quantum and classical predictions don't match, they are different. So before going into detail about the instrumental processes and the work itself, it is useful to have in mind what is the major application of this kind of studies. So the major application deals with certification protocols. So for example, if my goal is to generate a quantum state psi, and I have an experimental apparatus generating phi, and I want to know if the states are the same, if I'm generating the right state. How can I be sure that this happens, maybe without making any assumptions about the platform? So in other terms, can I design a device-independent protocol where my experimental apparatus is basically seen as a black box, so it isn't trusted, and I only can rely on input and output statistics. So as we learned also in a few talks in the previous days, a major role in this context is played by Bell's inequalities. So basically, in a Bell scenario, we have a bipartite state source, which is shared between two parties, Alice and Bob. And Alice and Bob can choose both between two operators. And if we look at the correlators between these operators, we can see that in a classical framework, this kind of linear combination, which is the well-known CH-SH inequality, is upper bounded by 2. While if I send an entangled state, the upper bound shifts to 2 times square root of 2. So what is interesting about these Bell inequalities is that, as many said before me, if you see a maximal violation of the Bell inequality, you are sure that your state is one of the maximally entangled states. So basically, this is a device-independent protocol which certifies that your state is maximally entangled. For example, the first the work in which the term device-independent was introduced is based on Bell's inequalities itself, and it is QKD protocol. So Bell's scenario can be seen in terms of causal modeling, so in terms of the causal correlations between the variables involved. And for example, it can be represented by a directed acyclic graph. So in a graph of this kind, we have the nodes, which are the involved variables, and those arrows, which identify the causal influence between the variables. So if I have an arrow directed from X to A, it means that X is having influence over A. So the graphic is directed because the arrows have a direction, and it is acyclic because you can't have loops. Because if A is affecting B, it means that A is in the past of B, and so B cannot influence A. Inside the graph, we have also some variables that we call hidden variables or latent variables, which are not observable. So there is a whole branch which is called causal inference, which was studied by Pearl in his book Causality. And the aim of causal inference is to tell whether some input-output statistics that we observe are compatible with some Bayesian network, so some causal structure. And Okay, and yeah, some causal structures are more interesting than others because they allow mathematical constraints between the variables. And so, from the input-output statistics, you can say, you can exclude that the observed data are from a certain causal structure. And what's even more interesting is that quantum and classical predictions can be different in cases like that. So, okay, Bayesian networks are a very versatile tool, so we can represent many different causal structures. And another example is, for example, the bilocality scenario, which has been studied very recently. And a few weeks ago, I think the group of John Wei Pan put an article on the archive closing the loophole of the independence of the measurement settings and the independence of the source. So it's it's a scenario that is being studied currently. And yeah, what we learned also Monday that Raphael said is that the bilocality scenario, the bilocality violation detects a form of non-local correlations that is smaller than a form of non-local correlations that is weaker than the one detected by the CHSH scenario. Because there are some probability distributions that violate by bilocality but don't violate the CHSH violation, inequality. So maybe we can look for another causal structure which maybe is simpler than the Bell scenario because the bilocality is more complex, it has more nodes. And maybe it is always, and maybe another scenario that is simpler also to implement in lab, which maybe doesn't require space-like separation between the parties, and which maybe detects the same set of non-local correlations as the CHSH. And the perfect candidate is the instrumental scenario. So the instrumental scenario is a widely used causal structure because it is used when we want to do the simplest thing that we can think when we are talking about causal inference, so causal inferences. So maybe I want just to know if a variable A affects a variable B or not. And variable A and B can be anything we want. For example, a medication and the recovery of a patient. But if I use this DAG here, this simple DAG, I cannot do anything because this DAG does not have testable application. It means simply that this DAG is compatible with any joint distribution of A and B. So I cannot tell whether A is really influencing B or not. So if I want to tell if A is influencing B, I need another causal structure, which is the instrumental structure, which is here. And that is currently used to test medications, for example. So in medication tests, you have a bunch of patients, and you decide some patients randomly to give a medication and some other patients to give a placebo, and then you can tell if the treatment is causing the recovery or not, even in presence of latent variables like genetic predisposition or anything else. And this causal structure has been studied again by Pearl in the 90s. So if I want to implement in lab this kind of structure, basically I have lambda, which is again a state generation source. I have two parties which don't have to be space-like separated because A must influence B. And so I have a variable x which chooses Alice's input, Alice's observable, and the output of Alice observable will choose Bob's observable. So in the classical framework, Pearl found those inequalities. So that's the instrumental inequality, which, so if it's violated classically, it means simply that I have not the instrumental causal structure. So it's like I was saying before, the instrumental allows for mathematical constraints between the variable, which allow me to exclude some probability distributions. If we go to the quantum realm, we see that if we want all the variables to be binary, there is no difference between the quantum and classical prediction. So we cannot violate any inequality going from the classical to the quantum realm. But what we showed, or what Raphael found, was that if X can assume 3 values, then there is a class of inequalities, of instrumental inequalities, which can be violated in the quantum realm. So yeah, the inequality that we used was that one. So the brackets indicate simply the expected values of the correlators, and the subscript means the value of X. And another inequality, which is equivalent to the first, is the Bonnet inequality, which is simply written in terms of the probabilities instead of the expected values. And yeah, if I send an entangled state to A and B, we see that the upper limit is shifted. So instead of being 3, it is 3.82. There is another limit for the Bonnet, which is like, instead of 2, it's 2.207. Yeah, and the maximum violation is always reached with maximally entangled states. So now that we have introduced the instrumental scenario, we may wonder what's the relation, if there is any relation, between the instrumental violation and the CH-SH violation. And this was studied by this guy here, that put a very nice paper on the archive. And so what they did was they noticed that the instrumental scenario can be seen as a post-selection of a classical Bell scenario. So basically what we do is we can run a CH-SH experiment and simply remove every event in which Y is different from A. Because again, in the instrumental you have that the output of A's measurement affects Bob's choice. So if we run a CH-SH experiment, we must remove any of these events and keep the events in which Y is equal to A. And then we can reproduce the statistics of the instrumental scenario. But now, I have said before that the CH-SH is violated when X is binary, but the instrumental is not. So we may ask, okay, maybe the instrumental scenario is detecting a stronger form of non-locality than the CH-SH, because there are some probability distribution which violate the CH-SH and not the instrumental. But the answer is no. They found that. Because, and they found that any non-classical correlation in the CH-SH can lead to violation of the instrumental inequality. So what we have to do if we want to actually see that these non-classical correlations are the same, we need to express the Bonnet inequality with these extended probabilities. So basically what we did is we only added Y and we put it equal to A, but the expression is the same as before. And from this expression, you can express the Bonnet inequality as a function of the CH-SH inequality. And if we want to compute this term with our CH-SH experiment, we need to map the probabilities between the instrumental and the CH-SH scenario in this way. So we keep the same probability when X is 0 and 1. And for the case that is missing, so X equal 2, we need to map the probability in this way. So basically we decide that when X is 2, A is equal to 0, which we can do. And so in this way we can evaluate all the probabilities with X equal to. In this case, this one would be 0. And so basically we have expressed the Bonnet inequality as a function of the CH-SH. So we can see that the non-local correlations that violate the CH-SH inequality are exactly the same of those who violate the Bonnet inequality. So they are detecting the same set of non-local correlation. So now that we have seen that they are equivalent, we can go to the experiment itself. So what we did was basically we implemented an instrumental scenario on a photonic platform, and then we tested this inequality here, which was the same I wrote before. So to do that, okay, we started with an entangled source of a source of entangled photon pairs, which is a type 2 BBO crystal, which generates the singlet. And we encoded the qubits in the polarization of the photons. So the Alice and Bob's measurement stations are simply a half-wave plate with then a PBS and 2 couplers that go to the detectors. But then to implement the arrow, which goes from A to B, so making the output of Alice influence Bob's choice, we needed to delay the photon of Bob through a roughly 160 meters long single mode fiber. So we had the time to measure the outcome of Alice and then swiftly change the operator of Bob. And to do that, we used a Pockels cell. So what we did was, okay, when the detector of Alice corresponding to output 1 reveals a photon, the signal is splitted and sent both to a coincidence counter, which reveals the event, and both to a driver of the Pockels cell, which applies a high voltage to the Pockels cell. So the Pockels cell, when it is on, it can behave, if you want, as a half-wave plate. So, and when it is off, it behaves like it performs the identity. So when we applied the voltage, we switched the operator that Bob was performing. And the Pockels cell has a time of reaction of the nanoseconds. So the delay here was sufficient. Okay, so now the results. I forgot to say that. Okay, we performed the experiment both with the feed-forward, the active feed-forward, so with the measurement of Alice actually influencing Bob, and both in post-selection. So in the other way, we never turned on the Pockels cell. We simply tried all the combination of the operators and then post-selected. So in post-selection, we obtained this violation, so 3.62. And in with the active feed-forward, so really switching on and off the Pockels cell, we obtained this other value, 3.335. That are the 4 cases. So we have the case, these 2 are the case of post-selection with and without corrections. And the other 2 are the cases of the active feed-forward on, with and without correction. And those are simply the value of the correlators. Okay, so in the end, in this work, we showed for the first time the violation of an instrumental inequality, which we thought it was very interesting because given the wide application of the instrumental processes, it is good, it is important to know how they behave when switching from the quantum to the classical to the quantum realm. And another interesting thing is that instrumental processes could represent a simpler platform for quantum information processing tasks because they are simpler to implement than the Bell scenarios. And yeah, so they could be applied to tasks like cryptographic tasks or randomness generation protocols. So thank you for your attention.
Okay, are there any questions?